At the close of the 19th century, physics stood at what many believed was its final moment of triumph. The laws of motion formulated by Newton, the theory of electromagnetism unified by Maxwell, and the thermodynamics developed to explain heat and energy seemed to form a complete and elegant description of the natural world. Universities taught students that the universe was essentially understood, governed by continuous forces and predictable equations. There was a quiet confidence that the remaining problems were minor, technical details rather than fundamental mysteries. This sense of completion, however, was an illusion. One of the most troubling problems emerged from the study of heat and light. When objects are heated, they glow, emitting radiation whose color and intensity depend on temperature. Physicists could measure this radiation with great precision, but when they tried to explain it using classical theories, the results were disastrous. The equations predicted that as the frequency of radiation increased, the energy emitted should grow without limit. According to mathematics, a hot object should release infinite energy in the form of high-frequency radiation. This prediction was not just wrong, it was physically impossible. Experiments showed a clear cutoff, a smooth curve that rose, peaked, and then fell. Nature refused to follow the rules that physics had confidently laid down. This failure became known as a crisis because it struck at the heart of classical thinking. The laws that worked perfectly for planets, bridges, and steam engines completely collapsed when applied to microscopic processes. Light, which had been so beautifully described as a wave by Maxwell's equations, suddenly behaved in a way those equations could not explain. The problem was not experimental error or missing data. It was a conceptual breakdown, revealing that the assumptions of continuity and smooth variation were no longer valid at small scales. The crisis was deeply unsettling for physicists of the time. Their worldview was built on the idea that nature was continuous, that energy flowed smoothly like water in a river. The notion that the universe might operate differently at microscopic levels threatened the unity of physics itself. Some hoped the discrepancy would disappear with better measurements or clever mathematical adjustments. Others sensed that something more radical was required, though few were ready to abandon the classical framework that had served science so well for centuries. This tension created an atmosphere of intellectual unease. On the surface, physics appeared strong and complete, but beneath that surface lay contradictions that could not be ignored. The inability to explain heat radiation was not an isolated problem. It hinted that the classical description of reality was fundamentally incomplete. The crisis forced physicists to confront a difficult possibility. The universe might not conform to human intuition or long-held mathematical habits. It was in this fragile moment that a quiet shift began to take place. The failure of classical physics did not arrive with dramatic explosions or sudden revolutions. Instead, it crept in through stubborn experimental results that refused to match theory. This slow, relentless mismatch prepared the ground for a transformation. The stage was set for an idea that would challenge continuity, redefine energy, and introduce a new scale into the laws of nature. From this crisis would emerge a single number, small in size but immense in consequence, that would permanently change how humanity understands the universe. As the 19th century drew to a close, the confidence of classical physics began to erode in subtle but undeniable ways. Laboratories across Europe were producing increasingly precise measurements, and instead of reinforcing established theory, these experiments exposed its weaknesses. The mismatch between theory and observation was no longer something that could be ignored or explained away. Every attempt to force classical equations to fit the data only highlighted how deeply flawed the underlying assumptions were. The crisis was no longer theoretical, it was empirical, visible in numbers written in lab notebooks and curves traced on graph paper. What made the situation particularly troubling was that classical physics had no internal warning system to signal its own failure. The same principles that explained the motion of planets and the behavior of electrical circuits were being applied faithfully to radiation, yet they produced nonsense. This suggested that the problem was not with calculation skill or experimental technique, but with the very idea that the same rules applied at all scales. The universe was sending a clear message: the laws governing the very small were not simply scaled down versions of the laws governing the very large. Many physicists resisted this implication. The success of classical mechanics had shaped not only equations but also intuition. Continuity felt natural, almost self-evident. Energy was assumed to vary smoothly, capable of being divided endlessly into smaller and smaller amounts. To question this was to question the philosophical foundation of physics itself. As a result, early responses to the radiation problem focused on patchwork solutions, mathematical tricks designed to preserve continuity while correcting the results. None of them worked. The growing sense of crisis had an important psychological effect on the scientific community. It created space for ideas that would previously have seemed unacceptable. When a theory works almost everywhere except in one stubborn corner, that corner becomes impossible to ignore. The study of heat radiation became that corner, a place where classical physics was forced to confront its own limitations. It was here that the illusion of completeness finally collapsed. This moment marked a turning point in the history of science. For the first time in centuries, physicists were compelled to consider that nature might be fundamentally discontinuous. The smooth clockwork universe imagined since Newton was beginning to crack, revealing a deeper, stranger structure beneath. The crisis was not merely about fixing an equation, it was about redefining what it meant to understand reality. In hindsight, this breakdown was not a failure but a necessary step forward. It exposed the boundary beyond which old ideas could no longer function. Without this crisis, there would have been no urgency to rethink energy, no motivation to introduce radical new concepts, and no opening for a new kind of physics to emerge. The collapse of classical explanations for heat radiation was the pressure that forced a revolution, preparing the scientific world for an idea that would forever change how the universe is described. At the center of this unfolding crisis stood a physicist who was, by temperament and training, an unlikely revolutionary. Max Planck was not a radical thinker seeking to overturn established ideas. He deeply respected classical physics and believed firmly in deterministic laws governing nature. His career had been built on the principles of thermodynamics, a field rooted in continuity and equilibrium. When the problem of heat radiation refused to yield to existing theory, Planck approached it not as a rebel, but as a craftsman searching for mathematical order within chaos. For years, Planck worked relentlessly to derive a formula that could accurately describe the radiation emitted by heated objects. Experimentalists had already mapped the radiation curve with remarkable precision. The shape of this curve was clear and repeatable, but no classical equation could reproduce it. Planck tried every known approach, adjusting assumptions, combining existing laws, and exploring new mathematical forms, all while remaining faithful to classical ideas. Each attempt failed. The data simply would not cooperate. Finally, in an act he later described as one of desperation, Planck made a move that went against his own instincts. He introduced a purely formal assumption that energy exchange between matter and radiation could occur only in discrete amounts proportional to the frequency of the radiation. This was not a claim about physical reality, at least not in his mind. It was a mathematical device, a trick designed to make the equations work. He assumed that energy was not emitted continuously, but in small packets. When Planck applied this assumption, something extraordinary happened. The equations suddenly aligned perfectly with experimental results. The radiation curve emerged naturally, without infinities or contradictions. For the first time, theory and observation matched across all frequencies. The success was undeniable, even if its meaning was deeply unsettling. To make the formula work, Planck had introduced a new constant, a tiny number that set the scale of these energy packets. This number, now known as Planck's constant, had no precedent in classical physics. What makes this breakthrough remarkable is that Planck himself did not fully believe in its physical interpretation. He saw the quantization of energy as a mathematical convenience rather than a statement about how nature truly behaved. In his own words, it was an act of desperation, not a philosophical commitment. Yet the mathematics did not lie. The constant was necessary, unavoidable, and universal. This moment represents one of the most ironic turning points in scientific history. A man trying to save classical physics instead exposed its deepest flaw by clinging to mathematical honesty and experimental accuracy. Planck opened a door he never intended to walk through. His equation worked not because it preserved old ideas, but because it quietly replaced them with something entirely new. The breakthrough did not arrive with dramatic declarations or bold predictions. It emerged quietly, embedded in a formula written on paper, yet within that formula lay a profound shift. Energy, once thought to flow smoothly and endlessly, now appeared to be fundamentally granular. A single constant, introduced almost reluctantly, had changed the rules of physics. Even before the scientific world fully understood what had happened, the universe had revealed one of its deepest secrets through mathematics alone. Although the equation worked flawlessly, its implications were slow to sink in. Planck himself announced his result cautiously, focusing on the accuracy of the formula rather than the strange assumption hidden inside it. To many of his contemporaries, the success of the equation mattered more than the meaning of the constant it contained. Physics at the time was still deeply rooted in classical thinking, and few were prepared to accept that energy itself might be fundamentally discontinuous. The new constant was treated as a parameter to be measured, not a signal of a coming revolution, yet the presence of this constant was impossible to ignore. It appeared not as a minor correction, but as a foundational element of the equation. Remove it, and the theory collapsed back into contradiction. Its value set a strict scale, determining how energy could be exchanged between matter and radiation. This was unprecedented. Classical physics relied on universal principles that did not impose such limits. Here, for the first time, nature seemed to enforce a minimum unit, a smallest step that could not be subdivided. As other physicists examined Planck's work, the deeper significance of the constant began to emerge. It was not tied to any particular material or experimental setup. It was universal, appearing wherever energy and frequency were related. This universality hinted that the constant was not an artifact of a specific problem, but a fundamental feature of reality. The equation did more than solve a technical issue. It quietly redefined what energy meant at the most basic level. The scientific community initially responded with caution and skepticism. Revolutionary ideas often enter science not with applause, but with silence. Planck's constant did not immediately overturn textbooks or inspire new theories. Instead, it sat uneasily within the existing framework, a small but stubborn anomaly. But anomalies have power. They force questions, provoke re-examination, and invite bold thinkers to explore their consequences. Within a few years, those consequences would become impossible to deny. The constant provided a key that others would soon use to unlock new mysteries of light and matter. What Planck had introduced as a mathematical necessity began to reveal itself as a law of nature. The breakthrough was no longer just a solution to a radiation problem, it was the first crack in the classical worldview. In retrospect, this moment marks the birth of modern physics. A single number, introduced reluctantly and without fanfare, began to reshape scientific thought. Planck had not set out to change the universe, yet his commitment to aligning theory with experiment forced him to accept a result that did exactly that. The constant he introduced became a boundary, a rule written into the fabric of reality, signaling that the universe operates on principles far stranger and more subtle than anyone had imagined. The introduction of Planck's constant did more than solve a single problem in radiation. It quietly announced the existence of a limit built into nature itself. For centuries, physics had been guided by the assumption that quantities such as energy, position, and motion could be divided endlessly. No matter how small a change one imagined, classical theory, allowed something even smaller. Planck's constant challenged this belief at its core. It suggested that there is a smallest meaningful scale for certain physical processes, a boundary beyond which the familiar concepts of classical physics simply stop working. At first glance, the constant looked harmless. Its numerical value is extraordinarily small, so small that its effects vanish in everyday experience. This is why the classical world feels smooth and continuous to human senses. A falling apple, a swinging pendulum, or a moving car all involve energies vastly larger than the scale set by this constant. In such cases, the discrete steps enforced by nature blur together, creating the illusion of continuity. But the smallness of the constant is precisely what makes it profound. It hides a fundamental rule in plain sight. The meaning of this limit becomes clearer when one considers what the constant actually measures. It links energy to frequency, tying together how energetic a process is with how rapidly it oscillates. This relationship is not optional or approximate, it is exact. Nature refuses to allow energy exchanges smaller than a certain amount for a given frequency. Below that threshold, the very idea of energy as a smooth variable loses meaning. The constant acts as a gatekeeper, deciding which physical descriptions are allowed and which are forbidden. This idea of a natural limit represented a radical departure from previous thinking. In classical mechanics, limits usually arise from practical constraints, not from fundamental laws. Friction limits motion, material strength limits construction, and measurement precision limits observation. Planck's constant introduced a different kind of limit, one that exists even in a perfectly ideal universe. It does not depend on technology, materials, or human capability. It is woven into the structure of reality itself. The presence of such a limit forces a rethinking of what it means to describe nature accurately. Classical physics relies on precise trajectories and exact values. But when Planck's constant becomes relevant, those notions break down. Energy can no longer be treated as a continuously adjustable dial. It behaves more like a staircase, allowing only certain steps. This is not a statement about human ignorance, but about how the universe operates. The limit is not something to be overcome, it is something to be respected. What makes this concept even more striking is that it applies universally. The same constant governs electrons in atoms, photons of light, and vibrations of matter. It does not care about scale, substance, or context. Wherever energy and frequency meet, the limit appears. This universality suggests that the constant is not merely a parameter, but a fundamental rule, as essential as the speed of light or the force of gravity. Max Planck himself did not initially interpret the constant in this philosophical way, yet its role as a boundary became increasingly clear as physicists explored its consequences. It marked the dividing line between the classical world of smooth motion and the quantum world of discrete events. On one side of the line, intuition holds; on the other, nature demands new rules. In this sense, Planck's constant is not just a number, but a declaration. It tells us that the universe has a minimum grain size for action, that reality is not infinitely divisible. This limit reshaped physics by forcing scientists to abandon comforting assumptions and confront a deeper, more constrained structure beneath appearances. The discovery of this boundary was one of the most important steps in humanity's journey toward understanding the true nature of the universe. Once this limit was acknowledged, its consequences began to ripple outward into every corner of physics. The idea that there exists a smallest unit of action meant that many classical concepts were no longer universally valid. Motion could no longer be described as a perfectly smooth curve at all scales, and energy could no longer be assumed to flow without interruption. Instead, nature appeared to operate with an internal resolution, a kind of built-in pixel size that defined what could and could not happen at microscopic levels. This realization forced physicists to confront a subtle but profound shift in thinking. In the classical worldview, laws were often seen as exact descriptions of reality itself. With the appearance of this fundamental limit, laws became conditional. They worked extraordinarily well in regimes where the constant's effects were negligible, but they lost authority when that scale was approached. Classical physics was not wrong, it was incomplete. It was an approximation, valid only when the graininess imposed by nature could be safely ignored. The limit also reshaped the relationship between measurement and reality. Before, it was assumed that any quantity could, in principle, be measured with arbitrary precision if instruments were refined enough. The constant suggested otherwise. At very small scales, attempting to probe finer details does not simply reveal more information. It changes the behavior of what is being observed. This was not a flaw in experimental technique, but a reflection of the universe's structure. The act of measurement itself became intertwined with the limits set by nature. As researchers explored these implications, they began to see that the constant was not merely a constraint, but also a guide. It indicated where new theories were required and where old ones would fail. It served as a warning sign, telling physicists when classical intuition could no longer be trusted. In this way, the constant became a compass, pointing toward a deeper framework that could accommodate discreteness without abandoning mathematical rigor. The philosophical impact was just as significant as the technical one. The existence of a fundamental limit challenged the long-held belief that reality could be understood through infinite refinement. It suggested that the universe is not an endlessly smooth continuum, but a structured system with built-in boundaries. This did not make nature less elegant. Instead, it revealed a different kind of elegance, one based on simplicity at the smallest scales and complexity emerging from it. Over time, this limit would become central to a new vision of reality. It explained why atoms are stable, why matter does not collapse, and why light behaves both as a wave and as a particle. None of these phenomena make sense without acknowledging the boundary imposed by this constant. What once seemed like an abstract numerical factor became a cornerstone of physical understanding. In the end, recognizing this limit changed the goal of physics itself. The aim was no longer to describe nature with infinitely precise classical paths, but to uncover the rules governing what is allowed and forbidden at the most fundamental level. The constant defined that boundary with quiet authority. It did not shout or announce itself dramatically, yet it permanently altered how scientists think about reality. By revealing that nature has a smallest scale of action, it transformed a simple mathematical insight into one of the deepest truths ever discovered about the universe. The idea that energy is quantized marked a decisive break from everything physics had assumed for centuries. Once Planck's constant entered the equations, it became impossible to maintain the belief that energy could change in an infinitely smooth way. Instead, energy appeared to behave in jumps, absorbed and emitted in discrete packets rather than flowing continuously. At first, this notion seemed almost absurd. Nothing in everyday experience prepares the mind for such behavior. Heat feels gradual, light appears smooth, and motion seems uninterrupted. Yet at microscopic scales, nature followed a different script. This realization gradually transformed from a mathematical curiosity into a physical principle. When energy exchanges were examined closely, especially in interactions between light and matter, the evidence became unavoidable. Atoms did not radiate energy arbitrarily. They emitted light at specific frequencies, producing sharp spectral lines rather than continuous bands. Classical physics had no explanation for this selectivity. Energy quantization provided a simple and powerful answer. Atoms could only exist in certain allowed states, and light was emitted or absorbed only when transitions occurred between them. The concept of quantization reshaped the understanding of atoms themselves. In the classical picture, electrons orbiting a nucleus should radiate energy continuously and spiral inward until the atom collapsed. Such a universe could not sustain stable matter. Quantization changed everything. Electrons were restricted to specific energy levels, and as long as they remained within those levels, they did not radiate energy at all. Stability, once mysterious, became a natural consequence of discrete rules imposed by nature. This new framework laid the foundation for what would soon be called quantum theory. It was not built overnight, nor by a single individual. It emerged step by step as physicists applied the idea of quantization to new problems. Light, once understood purely as a wave, began to show particle-like behavior when interacting with matter. Energy packets of light, later known as photons, explained why light could eject electrons from metals only above certain frequencies, regardless of intensity. Once again, classical expectations failed and quantization prevailed. What made this shift so profound was that it did not merely adjust existing theories, it redefined what a physical explanation looked like. Instead of continuous trajectories and deterministic outcomes, physics began to describe probabilities, allowed states and transitions. The laws no longer told particles exactly where to go, but rather what they were permitted to do. Nature was revealed not as chaotic, but as constrained by precise yet unfamiliar rules. As quantum theory developed, energy quantization proved to be its cornerstone. It explained chemical bonding, electrical conductivity, and the structure of solids. Technologies that define modern life, from semiconductors to lasers, rely directly on these principles. None of them could function in a universe governed solely by classical continuity. The discrete nature of energy is what makes controlled, predictable behavior possible at microscopic scales. Equally important was the philosophical impact. Quantization forced scientists to abandon the comforting notion that deeper understanding always comes from finer division. Instead, it suggested that there is a fundamental granularity to reality, a smallest unit beyond which division loses meaning. This was not a limitation of human knowledge, but a feature of the universe itself. From a single assumption about energy exchange grew an entirely new vision of nature. Quantum theory did not erase classical physics, it placed it within a broader framework, showing where it works and where it fails. The recognition that energy is quantized was the turning point that made this framework possible. It marked the moment when physics stopped trying to force the universe to behave continuously and began listening to what nature was actually saying. What makes Planck's constant truly extraordinary is not just that it introduced quantization, but that it quietly overturned humanity's most basic assumptions about reality. Before its discovery, the universe was imagined as a vast, perfectly smooth machine, governed by deterministic laws that left no room for ambiguity. Every effect had a clear cause, every motion a precise trajectory. Planck's constant shattered this picture, not by dramatic contradiction, but by revealing that the foundation itself was built from discrete pieces. This tiny number forced scientists to confront a universe that behaves differently depending on the scale at which it is observed. At human scales, the constant hides in the background, allowing classical laws to dominate. But at microscopic scales, it rises to authority, dictating what is possible and what is forbidden. Reality was no longer governed by a single, universal description, but by layered rules that emerged depending on scale. This realization alone reshaped how physicists thought about truth and explanation. One of the most unsettling consequences was the loss of certainty. Classical physics promised exact predictions if initial conditions were known. With Planck's constant at the heart of physical laws, that promise dissolved. Instead of precise outcomes, physics began to offer probabilities. The behavior of particles could be described only in terms of likelihoods, not certainties. This was not due to ignorance or experimental limitation, but to the structure of reality itself. The universe, at its deepest level, does not reveal exact answers, only statistically precise ones. This shift changed the meaning of measurement. Observing a system was no longer a passive act. At quantum scales, measurement interacts with and alters what is being measured. The constant sets the scale of this interaction, determining how much disturbance is unavoidable. The observer and the observed became entangled in a way classical physics never anticipated. Reality was no longer something that could be examined from a distance without consequence. Planck's constant also redefined the concept of causality. Events were no longer linked by simple, continuous chains. Instead, transitions occurred in jumps, governed by probabilities rather than certainties. This did not imply randomness without order, but a deeper kind of order rooted in statistical laws. Cause and effect still existed, but in a subtler form, mediated by the constraints imposed by quantization. Beyond physics, the philosophical impact was immense. The constant challenged the idea that the universe is fully comprehensible through direct intuition. It suggested that human experience, shaped by macroscopic continuity, is a poor guide to the fundamental nature of reality. To understand the universe, one must accept ideas that feel abstract, counterintuitive, and even paradoxical. Reality, it turned out, is not obligated to make sense to everyday perception. The influence of this shift extends far beyond theory. Modern technology depends on embracing this strange new reality. Electronics, medical imaging, communication systems, and countless other applications work precisely because engineers rely on quantum principles rooted in Planck's constant. What once seemed philosophically troubling became practically indispensable. In revealing a universe governed by limits, probabilities, and discrete rules, Planck's constant changed more than equations. It changed the questions scientists asked, the methods they used, and the expectations they held about knowledge itself. It taught humanity that the universe is not a smooth, predictable clockwork, but a layered and nuanced structure where certainty gives way to probability and simplicity emerges from constraint. That realization reshaped not only science, but our understanding of what it means to know the universe at all. One of the most remarkable aspects of Planck's constant is how far its influence extends across the universe. What began as a solution to a narrow problem in heat radiation turned out to be a universal rule that applies everywhere, from the smallest scales of atoms to the vast processes unfolding in stars. This constant does not belong to a single theory, object, or environment. It operates silently and consistently wherever energy, matter, and radiation interact, making it one of the most far-reaching numbers ever discovered in science. At the atomic level, Planck's constant governs the structure of matter itself. The arrangement of electrons around atomic nuclei, the stability of atoms, and the way atoms bond to form molecules all depend on quantized energy levels defined by this constant. Without it, electrons would not occupy fixed states, atoms would not have well-defined sizes, and chemistry as we know it would not exist. The richness of the material world, from water to DNA, is rooted in rules shaped by this single number. Moving beyond individual atoms, the constant plays a decisive role in the behavior of solids and liquids. The electrical properties of materials, such as conductivity and insulation, arise from quantum effects controlled by Planck's constant. Semiconductors, which form the backbone of modern electronics, rely on precise energy gaps that exist only because energy is quantized. Every computer chip, smartphone, and digital network is built on principles that trace back to this constant's quiet authority. Light itself is equally bound by this rule. The colors we see, the way light is emitted by hot objects, and the interaction between light and matter are all shaped by the relationship between energy and frequency defined by Planck's constant. In astronomy, this relationship allows scientists to determine the composition, temperature, and motion of distant stars and galaxies. By analyzing light that has traveled millions or even billions of years, researchers rely on quantum rules that were first hinted at in a laboratory on Earth. The reach of the constant extends even further into the extreme environments of the cosmos. In the hearts of stars, nuclear reactions release energy according to quantum principles. The balance between gravity and radiation that keeps stars stable depends on processes governed by this constant. Even the life cycle of stars, from their birth in clouds of gas to their eventual collapse or explosion, is influenced by quantum effects operating under its rule. What makes this universality so profound is its indifference to scale and context. The same constant applies whether one is studying an electron in a laboratory or radiation from a distant quasar. It does not weaken with distance, change with conditions, or depend on location in the universe. This suggests that Planck's constant is not an emergent feature, but a foundational element of reality itself, present wherever physical laws apply. Its influence also reaches into the most advanced frontiers of physics. Attempts to understand the earliest moments of the universe, the nature of black holes, and the structure of spacetime itself all involve this constant. It appears alongside other fundamental constants in equations that aim to describe reality at its deepest level. Any future theory that hopes to unify gravity with quantum mechanics must account for its role. In this way, Planck's constant serves as a unifying thread running through nature. It connects the behavior of the very small with the behavior of the very large, revealing that the universe operates under a coherent set of rules across all scales. A number once introduced to fix a technical problem became a universal key, unlocking insights into atoms, stars, and the structure of the cosmos itself. The story of Planck's constant ends not with triumph, but with quiet irony. The man who introduced the number that would transform physics never intended to overturn the foundations of science. Max Planck was deeply committed to classical principles and spent much of his life believing that nature was ultimately deterministic and orderly in the traditional sense. Yet his legacy became inseparable from a revolution that challenged exactly those beliefs. This contrast between intention and outcome is what makes the discovery so powerful. In the years following his breakthrough, Planck watched as younger physicists took his constant far beyond its original purpose. Ideas built upon it began to reshape the understanding of light, atoms, and matter itself. Each new success of quantum theory pushed physics further away from the classical worldview that Planck had tried to preserve. For him, this was both a validation of his work and a philosophical discomfort. He accepted the results because they were correct, even when they contradicted his intuition. This commitment to truth over comfort defines scientific integrity at its highest level. The transformation of physics that followed was not immediate, nor was it smooth. The new ideas sparked debate, confusion, and even resistance. Many scientists struggled to accept a universe governed by probabilities rather than certainties. Yet the predictive power of theories built on Planck's constant could not be denied. Again and again, experiments confirmed results that classical physics could not explain. Gradually, resistance gave way to acceptance, not because the ideas felt right, but because they worked. What makes this story enduring is that it illustrates how scientific progress often occurs. Revolutions do not always come from bold rebels intent on change. Sometimes they come from careful thinkers who follow logic wherever it leads, even when it leads somewhere uncomfortable. Planck did not seek to change the universe, he sought to describe it honestly. In doing so, he revealed a deeper structure that no one had anticipated. The constant that bears his name became more than a technical parameter. It became a symbol of a new way of understanding nature. It marked the moment when physics accepted that reality at its core does not conform to everyday intuition. The universe revealed itself as layered, constrained, and subtle, governed by limits that cannot be bypassed. This realization reshaped not only equations, but expectations about what science can and cannot promise. Planck lived long enough to see the full impact of his work, including the rise of quantum mechanics as a central pillar of modern physics. He witnessed a new generation embrace ideas that once seemed unthinkable, and he saw how his reluctant assumption became a foundational truth. His journey serves as a reminder that the consequences of discovery often extend far beyond the intentions of the discoverer. In the end, the story of Planck's constant is a story about humility before nature. It shows that the universe does not bend to human preference or intuition. When evidence demands change, understanding must follow, no matter how disruptive that change may be. A single number, introduced to solve a narrow problem, ended up rewriting humanity's picture of reality. This is why Planck's constant stands as one of the most important discoveries in science. Not because it was dramatic at first glance, but because it quietly forced a transformation that could not be undone. It reminds us that the deepest revolutions often begin with small steps, careful reasoning, and the courage to accept results that challenge everything we thought we knew about the universe.